sleep and study. Don't forget to subscribe.
Elementary particles. It's intuitive to understand what that means. It's something so fundamental that you can't break it down further. You can't discover what that particle consists of. Historically, this concept has been evolving over time. At one point, atoms were thought to be the most elementary particles. Since the time of the ancient Greeks, it was evident to people that the world is made up of some smallest elements, and atoms were believed to be those fundamental elements. However, that continued until we could delve into the atom. Roughly a century ago, Rutherford, by bombarding a tin foil with alpha particles, found out that atoms are largely empty. He discovered that in the center of the atom is what we now refer to as the atomic nucleus, which is approximately 1,000 times smaller than the atom itself. So I suppose you might say that elementary particles are atomic nuclei. Yet there had to be something more than just atomic nuclei, which possess an electric charge, while atoms themselves are neutral. And this something else was named the electron. So we have two elementary particles, the nucleus and the electron, but that wasn't all. Soon it became clear that the nuclei of different atoms were actually composed of other components. They aren't single elementary objects. Around 36 years into the last century, Heisenberg in Germany and Ivanenko in Russia suggested that nuclei consist of two elementary particles, the proton and the neutron. And we already have three elementary particles, a proton, a neutron, and an electron. For a long time it was like that, but during this time quantum mechanics was born. The science that actually explained how the atom is organized, why the electron, rotating in stationary orbits around the nucleus, does not fall on this nucleus. In fact, according to the laws of classical physics, the electron, as an electrically charged particle, should have been emitting light all the time, losing energy and falling very quickly to the nucleus. This is not happening, and the reason for this turned out to be that the electron follows the rules of quantum mechanics. Hence, the three elementary particles, the proton, neutron, and electron, appeared to construct the entire world visible to us. However, a natural question emerged. Why aren't these particles dispersing in various directions? Why don't two protons, each carrying a positive charge, repel each other and fly apart due to the Coulomb force? Why are they so tightly bound to the neutrons within the nucleus? Here's another question. If these are truly elementary particles, and they are not composed of anything, and nothing can affect them, then logically they should exist forever. However, the neutron, as it turns out, decays rather quickly. It transforms into a proton, an electron, and another elusive particle. This elusive particle was detected by the missing energy. In other words, if you measure the energy of the electron, the proton, and the energy of the original neutron, it turned out that some unexplained energy was missing. Pauli suggested that this was a new elementary particle. At the time, it was completely revolutionary because it was thought that there were no new elementary particles. We already understood everything, but it turned out not to be so. Pauli suggested that there was a small particle that carried no electric charge and had an extremely small mass. Fermi proposed calling it a neutrino. And so the number of elementary particles began to grow. The proton, neutron, electron, and neutrino are fundamental particles. The neutron decayed into a proton, an electron, and a neutrino. Well, technically, antineutrinos, but that's not crucial at the moment. However, that wasn't everything. There needed to be a force to bind the protons and neutrons together, and it certainly wasn't the electric force, as that is far too weak. The Japanese physicist Yukawa proposed that there was another elementary particle responsible for the nuclear forces, which are the forces that hold protons and neutrons together within the nucleus. He proposed that there might be another kind of elementary particle, and that nuclear forces exist because of the exchange of these new elementary particles, which were eventually named pi mesons, or pions. The Greek letter pi was used for them. As a result, the number of known elementary particles started to gradually rise. Shortly thereafter, a heavy electron was discovered, which was later named the muon, and physicists began exploring cosmic rays. Cosmic rays are a form of radiation that reaches us from the depths of outer space. protons, electrons, antiparticles, and quite surprisingly, some very peculiar objects are flying towards us. Back in 1947, scientists discovered a new elementary particle in cosmic rays, which was named the K-meson. This particle exhibited some very strange properties. There were three types of mesons. One carried a positive charge, another had a negative charge, and the third one was neutral. Now, these three particles acted in a rather peculiar manner, which led to them being referred to as having strangeness. It was believed that they possessed a novel property termed strangeness. Consequently, researchers started to investigate these peculiar particles. It was discovered that K-mesons were not the sole particles exhibiting strangeness. Over time, the count of such particles began to increase. In cosmic rays, particles arrive that can have a prolonged lifespan. If their lifespan is brief, they manage to decay before reaching us from space. The question arises, how long do these elementary particles live? What do we know about them so far? Well, the electron, as it appears to us now, lives forever. We don't know how it can decay. The fact is that the electron is by far the lightest particle with an electric charge. And so, by virtue of the law of conservation of energy, it simply has nothing to decay into. That's why, according to current thinking, the electron lives forever. The proton, however, might decay generally speaking. But up to now, we know that its lifetime, as measured experimentally, is greater than 10 to the 34th power of years. To put that in perspective, the age of the universe is about 10 to the 10 years. So, practically speaking, the proton lives forever according to those standards. Whether it decays in the end remains an open question. This is something that experiments must determine to see if it decays or not. The theory suggests that protons can decay. As for neutrons, they have a short lifespan, decaying into protons, but within nuclei. Neutrons last almost indefinitely due to a reverse transformation process from protons to neutrons. Moving on, the K-mesons and pi-mesons I mentioned have brief lifespans. They last around 10 to the minus 6 seconds, or 10 to the minus 9 seconds. By human standards, they decay almost instantly, but by the standards of particle physics, they live quite a long time. To this, we should also add that they move with very high speed, coming to us from space, that is, at a speed close to the speed of light. And according to Einstein's special theory of relativity, time slows down for fast-moving objects. Therefore, their own time flows very slowly, practically standing still. And so these particles, despite the fact that at rest they should have decayed in elusive fractions of a second, actually live quite long enough to come to us from outer space. But cosmic rays are sources of new particles, new elementary particles. They were once discovered there, and the number of them began to gradually increase, more and more and more. Then these particles would be discovered on accelerators. And we had a whole zoo of these particles. Particles began to be called by Greek letters. And there appeared rho mesons, omega mesons, eta mesons, psi mesons, sigma mesons, and so on, and other particles. The amount of particles grew so vast that there was a natural urge to categorize them in some way, similar to the Mendeleev table. In the Mendeleev table, as is well known, all elements are classified excellently, divided into periods and series. And now, due to quantum mechanics, we comprehend how they are organized and why there is this classification of chemical elements. Similarly, with elementary particles, we also wish to classify them somehow, given their large number. Naturally, we have to look at the properties of these particles, how they differ, and try to somehow divide them into separate classes according to their properties. One of such remarkable properties turned out to be the presence of angular momentum in particles. That is, from a classical point of view, particles are classically something like spinning tops. That is, they rotate with a very large angular momentum. It is not possible to describe this angular momentum classically. If the particle possessed a certain size and this angular momentum, which we measure, then it would result in the surface of this particle rotating at a speed exceeding the speed of light, which is impossible. So, in classical physics, you cannot describe this type of rotation. It is only possible within quantum mechanics. Interestingly, in quantum mechanics, this angular momentum is quantized. This means that you can only take on integer or semi-integer values measured in specific units known as Bohr magnetons. Therefore, it turns out that all particles can actually be divided into two distinct classes, those with whole angular momentum and those with half-integer angular momentum. These particles have two different names. Particles with integer angular momentum are called bosons, because when they gather in large numbers in some kind of ensemble, they obey a statistic called Bose-Einstein statistics. And particles with half-integer angular momentum behave in a completely different way. They obey a completely different statistic. This statistic is called the Fermi-Dirac statistic. It turns out that particles with integer spin and those with half-integer spin are actually two completely different classes of particles. Now, if we consider the particles I've mentioned before, such as protons, neutrons, electrons, and neutrinos, they are all fermions. This means they are particles with spin 1/2. However, pi mesons and k mesons possess spin 0, which classifies them as bosons. Moreover, a particle with spin 1 is a rho meson. Interestingly, light is quantized too, and the quantum of light, which is the photon, also has spin 1, making it a boson as well. So, the first classification is ready. We have fermions and we have bosons. We've divided the particles into two classes with very different properties. But that wasn't enough. It turns out that particles, in addition to having angular momentum, they interact with each other. One of the interactions we know well is electricity. They have an electromagnetic interaction. They have an electric charge. So we have particles with a positive charge, a negative charge, and some with zero charge. However, it turns out that besides that, particles are also involved in other types of interactions. For instance, protons and neutrons are influenced by the nuclear forces that bind them together. Here we encounter another classification. Some particles engage in the strong nuclear force, while others do not. The particles that engage in strong interactions are referred to as hadrons. Hadron comes from the Greek word hadros, meaning hard or heavy. All particles involved in strong interactions are heavy particles. Another class of particles doesn't participate in these interactions, like the electron. These lighter particles are called leptons, from the word leptos, meaning light. So, there are heavy particles, hadrons, and light particles, leptons. It turns out that all the particles we encounter in nature can actually be divided into two main classes, hadrons and leptons. Besides that, there are particles which are bound together by interactions. A good example of this is the photon. These particles fall into a special class known as the class of interaction carriers. They include the photon, as I mentioned, but it was later discovered that every other interaction is also carried by particles. Particles such as the so-called intermediate vector bosons, gluons, gravitons, and others emerged. These represent a novel class of particles, unified by interactions. Therefore, when considering their physical properties, we categorize all particles into three distinct classes: strongly interacting hadrons, weakly interacting leptons, and carriers of interaction. However, the story doesn't conclude here. It was eventually found that hadrons are not genuinely elementary particles, as they were later discovered to be composed of even smaller objects, which eventually came to be known as fundamental particles, differing from what we now call elementary particles in the aptitude terminology. The particles that compose all hadrons were identified as particles known as quarks. Consequently, the new fundamental particles, or elementary particles if you prefer, were recognized as quarks, from which all hadrons are constructed, and leptons, which currently do not exhibit any such internal structure and are, in our current understanding, genuinely elementary. So we possess a specific number of quarks and a certain number of leptons. Here are the interaction transfer particles that I previously mentioned. These particles are, without a doubt, the most elementary, indivisible, and fundamental particles. But how can you determine what an elementary particle consists of? How can you look inside an elementary particle to see if there's something within it? It's impossible to view it under a microscope. So we have to somehow figure it out. What would we do if we wanted to understand how some other object functions? Oddly enough, we try to break it. Consider a watch, for example. We look at a watch and we can see the components inside it. But if we break the watch open, gears will spill out, some wheels will come out, and then we can understand how the watch is put together. Now, what about the elementary particle? It turns out that the quantum world operates in a different way. It turns out that there's actually nothing inside an elementary particle. Maybe even nothing at all. We don't even understand yet if there is any structure to the elementary particle. But still, how do we actually get into it? The method that has been discovered is to accelerate this particle to a very high energy if possible, and then hit some target. If we hit some target, amazing transformations begin and new particles are born. And quite interestingly, it isn't that these new particles are actually inside the particles we collide or within the target. No, not at all. They are actually created from the energy of the collision itself. There's a remarkable Einstein formula at play here, which states that the rest energy of a particle equals mc squared, meaning mass times the square of the speed of light. When we accelerate a particle to extremely high energy and collide such particles, new particles can emerge from this collision energy, with energy that is less than the kinetic energy, or whose mass is less than the kinetic energy to which we've accelerated the particles. So the device that accelerates particles to very high energies is called a particle accelerator. And these accelerators have been around for a very long time. The simplest accelerator is an electric field. If you have an electric potential or potential difference, then electric charged particles will move in this potential and accelerate. The magnetic field works in the same way. So essentially, we're using electromagnetic interaction, electric magnetic fields, to accelerate particles. Well, the simplest is some kind of capacitor with a potential difference. And so that will accelerate the particles a little bit. But we would like to accelerate the particle not just a little bit, but to accelerate it to very high energies. But cosmic rays are such a natural accelerator. Cosmic rays come from far away. But since cosmic rays have few particles, studying them is hard, even though the universe was the first accelerator. So scientists decided not to rely on the universe and learn to accelerate particles themselves. They began constructing an accelerator. It's obvious that if the length over which a particle accelerates is short, it won't gain much energy. This led to the concept of a ring accelerator. So the particle would keep moving faster and faster around the ring, with the electric or magnetic field constantly urging it on. That's similar to how a trainer encourages horses in a circus arena. The particle will keep accelerating more and more rapidly. These initial accelerators were developed in the middle of the last century. They were known as cyclotrons, and their goal was to achieve the maximum energy of particles, meaning to accelerate them to the highest possible speed. Accelerator energy is quantified in units known as electron volts. An electron volt represents the energy gained by an electron as it traverses a potential difference of 1 volt. Thus, it is named electron volt. Consequently, accelerators accelerated particles to millions of electron volts. Initially, these accelerators were measured in these units, commonly abbreviated as MeV, and therefore, particles were accelerated to several MeV. That's millions of electrons volts. That's actually quite a lot of energy, and the speed of the particle, it's already starting to approach the speed of light. What happens next? The next thing you can put in the path of this particle is a target. Just a piece of some metal or some gas or something. And the particle hits that target. At the moment of impact, colossal kinetic energy of the particle is released, and from this energy new objects are born, new particles are born. So particles have been discovered that we didn't know we had. That is, in fact, what was born there was just unclear, and we had to study the products of this very interaction. How do you study them? How to see what was born at the accelerator? It is desirable to fix the particle somehow. The place where the particle is fixed or detected is usually called a detector. At first, the detectors were photographic films, photographic emulsions, on which the particle left a trace. Then there were some types of gas chambers, where a magnetic field was applied and the particle left a mark, similar to the reverse trail of an airplane in the sky. However, over time, in modern times, we are transitioning towards computerized recording of the activities happening there. Detectors have become extremely large, and the modern detector at the Large Hadron Collider is comparable to a 4-story building. Everything is meticulously recorded in this detector. The particle's momentum, the angle at which it exits, and the charge of the particle are crucial. There are specialized detectors that identify light particles, such as leptons. Additionally, there's a unique detector for capturing hadrons. In summary, it has evolved into a massive industry. Moreover, the accelerators themselves have been continuously boosting their energy levels. In Russia, or more precisely in the Soviet Union, accelerators were constructed during their time, and the first cyclotrons emerged in the post-war years. As time progressed, this accelerator science was further developed, with the ongoing mission to continually increase the energy of particles. In Dubna, which is located near Moscow, a synchrophasotron was constructed. This was the name given to the accelerator, which was built on a new principle known as autophasing. This principle involves the magnetic field that drives particles to accelerate more and more and automatically synchronize their phase. As a result, the particle was accelerated to extremely high energies. This is a synchrophasotron constructed at the end of the 1950s in Dubna, which accelerated particles to energies of 10 billion electron volts. Of course, there were similar accelerators in both Europe and the United States, and there was a sort of competition to determine who could achieve higher energy levels. The next significant machine built in the Soviet Union was the Sarpukov accelerator, with an energy level reaching 70 billion electron volts. That is actually 7 times larger than Dubna. However, this record was not maintained for a long time. Just a few years later, an accelerator was constructed to achieve 400 billion electron volts, or 400 GeV. Nowadays, modern accelerators have become even larger. Accelerators are categorized into 2 additional classes. These are accelerators that are designed to accelerate electrons, and those that are designed to accelerate protons. Both of these particles, as well as others, have a very long lifespan, so nothing happens to them, allowing them to be accelerated effectively. As we move along the ring of this enormous accelerator, the rings keep expanding and getting larger in size. For instance, if the Dubna accelerator has a radius of roughly about 20 meters, the Serpukhov accelerator's radius is already around 200 meters. Then consider the ring of the accelerator in Geneva, where initially the electron accelerator was constructed, followed by the proton accelerator. This ring has a circumference of approximately 27 kilometers, which is about the same size as the ring line of the Moscow metro. So the accelerator becomes an enormous structure. But why do we need to construct such a large accelerator? Why is this size necessary? The reason is that to achieve higher energies, we constantly require a larger magnetic field to keep the particles on the ring, or they'll just escape. The smaller the accelerator's radius, the more the particles need to be wrapped around, requiring a stronger magnetic field. Generating strong magnetic fields is a tough technical challenge. Thus, if you construct the accelerator with a larger radius, you can manage with weaker magnetic fields, which explains the size of the accelerator. However, that's not the only reason. Another reason is that as charged particles like electrons and protons travel around the accelerator ring, they emit light known as synchrotron radiation. So, the more the electron becomes wrapped up, the more it emits light and loses energy. Eventually, the energy loss will match the energy we input to accelerate the particles. Therefore, there is a natural limit to this process. By increasing the radius of the accelerator, we can reduce these energy losses, allowing us to accelerate the particle to even higher energies. Thus, by accelerating particles to high energies, our goal is to increase the radius of the accelerator, minimizing the energy losses. So the accelerators are very large, and these accelerators accelerate particles that then hit a target. It's called a fixed target accelerator. But it was soon realized that a lot of the accelerator's energy is wasted just by the particles hitting the target, trying to move the target out of place. And essentially, the energy goes into the motion of the target molecules, which is heat. So take a very large amount of energy is lost that could have gone into the formation of new particles. And the idea of colliders was born. A collider is when there is no fixed target, when we accelerate two beams of particles and they collide with each other. And so modern accelerators like this are basically colliders. For example, the Large Hadron Collider in Geneva, which is now operating, and at which there have already been discoveries that we are expecting new discoveries, is a collider. There are two proton beams collide, meaning protons are accelerated in opposite directions within a ring, and they meet at the intersection points of these rings, forming what is known as a collider. The challenge with colliders, naturally, is ensuring that these two very narrow beams don't just pass by each other but actually collide. Therefore, the beams need to be focused very precisely. This presents a significant technical challenge, which fortunately has been resolved. Now the collider is operational. In Geneva, where the Large Hadron Collider is, protons collide. Before that, electron-positrons collided in the same ring. It was an electron-positron collider. So the modern accelerator is a collider. But there's another type of accelerator, linear accelerators. In a linear accelerator, there's no ring. Particles first accelerate in ring accelerators, then go directly out onto the road like the speedway, and they are already moving swiftly towards one another. If, because of special technology, a very large acceleration gradient is provided, then even though they pass through this speed segment just once, these particles manage to accumulate an immense amount of energy and collide with one another. In this scenario, there are no energy losses. As the particles do not execute any turns, they simply collide directly with each other. This is the linear collider. Linear colliders exist, but now there's a big project for an international linear collider, 50 kilometers long. The length is set to achieve high energy. The longer, the more energy. There is a project for this international collider, and construction might start in Japan in a few years. Every accelerator has its pros and cons, naturally. However, its main role is to speed up particles to maximum energies. The current acceleration records are 200 billion electron volts for electrons and positrons in the Large Ring Collider, known as LEP, the Electron-Positron Collider in Geneva. For Hadron Colliders, the record is held by the Large Hadron Collider, where protons reach an energy of 7 trillion electron volts. This represents the highest energy currently achievable, enabling the creation of particles with large masses that were previously inaccessible to research. The first example of this was the discovery of the Higgs boson at the Large Hadron Collider. At present, physicists are hopeful that this is not the end, and that new particles will continue to be discovered. Hadrons, strongly interacting particles. There was a time when hadrons were few, the proton, the neutron, and the pion proposed by Euclid. But then it became a lot, and some kind of classification was needed. And the first classification is quite obvious. It's related to angular momentum. It turned out that all hadrons either have a whole angular momentum, intrinsic angular momentum, or spin, as it is commonly called, or semi-integer. Hadrons with half-integer angular momentum are called baryons, and hadrons with integer angular momentum are called mesons. So here we have the world of baryons and mesons. So a proton, a neutron are baryons, a pi meson is a meson. It turned out that there were a lot of them, and we had to figure out how it all worked, and why there were a lot of them, and how they were arranged. And when there were about 100 of them, it was clear that this classification was not just to arrange them into classes, but to explain their properties. And it turned out that there were some very interesting mathematical schemes that particles fit into. This is somewhat unexpected, and it's called the math of group theory. In general, the concept of a group in mathematics, of course, it should be explained somehow, but intuitively it is clear that if there are some transformations that we can do, well, for example, to turn on one leg around ourselves, this is the transformation that we have made. It is clear that if we turn around once or turn around the second time, it is the same as turning around twice. These are the kind of transformations, they're called group transformations. So I'm explaining it a little bit primitively, but actually a group is a transformation that can be done one way and another way. And this is equivalent to a third way. There's an inverse transformation, which is to turn on your foot in the opposite direction, or a singular transformation, which is not to turn at all. And so these all form what in mathematics is called a group. Groups are all classified. There are a finite number of them. They have a certain size, certain properties. And it turned out that hadrons can all be classified mathematically by group theory. There are certain special groups of matrices. Matrices are essentially tables. Now, let's envision a 2x2 element table. It has 2 columns and 2 rows. That's what we call a matrix. Interestingly, there exists a group of transformations related to these matrices. Hadron particles actually occupy the elements within these matrices. In other words, there are these tables. And particles fill the elements of these matrices. These tables can be 2x2, 3x3, or even 4x4. If we correctly guess the group, it allows us to determine the number of elements present in the table. This implies that particles must occupy those elements. If a particle isn't present, yet the table exists, we should attempt to discover a new particle that precisely completes this matrix. That was essentially the approach that was taken. These tables or matrices are connected to a group known as the special unitary non-modular group with 3 elements called SU3. So it turned out that all particles can be arranged in tables according to this group. These tables form 8s, 9s, 10s, and here all particles sit in these elements. And it turned out that all hadrons can be arranged in this successful way on these elements of the matrix. So new hadrons were predicted to fill the voids in these tables, and it would seem that we finally understood how the world of baryons and mesons works. Baryons got into their tables, mesons got into other tables, and everything seemed to fall into place. But then suddenly some particles began to appear which did not get into these tables. And it turned out that the tables were probably not complete. And on the other hand, it seems that if there are tables, then there should be some maybe clearer understanding behind it. And if there are about 100 particles, then of course the same question arises as it arose in atomic physics. If there are about 100 atoms, and chemical particles, elements, perhaps they're composed of simpler parts, like assembling elements from toy blocks, like atomic nuclei. There are about 100 made from protons and neutrons. Combine a certain number of protons and neutrons and you form an atomic nucleus. It's similar with hadrons. These tables, these symmetries as they're called, relate to the existence of smaller objects from which hadrons are constructed. Initially, these objects were viewed merely as a mathematical toy, since the mathematical group encompassed everything. And here's a sort of mathematical toy. 2 individuals actually proposed these objects. One of them suggested naming them aces. He probably enjoyed card games, so the terminology reflects it. Interestingly, when he authored a scientific paper proposing a classification of all hadrons using these aces, it was rejected for publication in a journal, with the explanation that a card game was just a card game. The terminology just doesn't quite fit. Another person suggested calling them quarks. Quark is indeed a peculiar word. It originates from James Joyce's novel Finnegan's Wake, where there's a poem that reads, 3 quarks for Mr. Mark. Now that's certainly an odd word. Quark was adopted by Marie Gallman, the Nobel laureate responsible for this classification. Meanwhile, the other physicist, George Zweig, who proposed calling them aces, found that his terminology didn't gain popularity. The terminology quark took hold, and so it turned out that this whole classification of all hadrons could be understood by assuming that they were made up of smaller particles called quarks. And at that point, there were 3 quarks. It turned out that all baryons, that is, particles with spin, all hadrons with spin half integer, are built from 3 quarks, and all mesons, that is, particles with spin whole, are built from 2 quarks. It turned out to be very simple. There are 3 types of quarks, and out of them the whole world is built, all strongly interacting particles. Some are made of 3 quarks, others of 2 quarks. This quark scheme immediately explained the structure of these matrices in which hadrons were put, and it turned out that strongly interacting particles, elementary particles, they are not really elementary, they are made of quarks. Everything revolved around quarks. Soon quarks were recognized as real particles, not just a mathematical scheme. The point is that in hadron scattering experiments at accelerators, very similar to Rutherford's experiments when he bombarded the foil and discovered the atomic nucleus. So in the scattering experiments, it was found that really inside the baryons there are like 3 grains, 3 quarks, and inside the mesons there are like 2 grains, 2 quarks. That there are quarks, these are really the kind of particles that are inside. But the amazing property of these particles is they never fly out. This property is not yet fully understood, but it has been established quite accurately that these particles are always somewhat captive inside the hadron. It turns out that there are 3 of them inside the baryon, but they never escape. They are held together by very strong forces, and when they attempt to move in different directions, these quarks are resisted by forces like stretch springs that do not allow them to separate. If this spring breaks, a new quark is created at the end, leading to the formation of new hadrons. So, from one hadron, many hadrons emerge in an interaction. Each one is composed of quarks. This is how the world of hadrons came to be understood through the quark model, which has been extensively developed and confirmed over time. For a significant period, there were 3 types of quarks known as top, bottom, and strange. These 3 quarks were recognized until new particles were discovered that didn't align with the existing scheme or matrices. It turned out that explaining them required the introduction of a 4th quark. This line of research continued to develop, although I don't want to delve further into quarks at the moment. However, the structure of hadrons began to emerge quite clearly. If hadrons are composed of quarks, then it is necessary to consider all possible combinations, and all these combinations must exist. Interestingly, all hadrons are indeed composed of either 2 or 3 quarks. The question arises, why not 4 or why not 5? These are the kind of hadrons that were subsequently discovered as well. Although they are not as reliably discovered as ordinary hadrons, they are called exotic hadrons. This is something that is a hot topic right now. Exotic hadrons built from 4, 5, or maybe 6 quarks. So what happens to hadrons when they collide at accelerators? Here we say Large Hadron Collider, hadrons collide there. In this case, we're talking about a proton collision. The proton is the simplest hadron, the baryon. It consists of 3 quarks. What happens when 2 hadrons collide in accelerators? It would seem that they should sort of flatten, the quarks should come out. But this does not happen by virtue of the amazing property of quarks, by virtue of the interactions that bind quarks to each other. It turns out that when 2 hadrons collide, they create new hadrons. These newly formed hadrons fly out at high speeds in the form of jets. From a large number of hadrons in just one event, a massive number of particles are produced. If the initial protons have high energy, even more heavy hadrons are created. Interestingly, some of these particles can be extremely heavy, with masses comparable to that of an average atom. But all these hadrons turn out to be short-lived. And since they're heavy, they tend to decay very quickly. Decay times vary enormously, from 10⁻⁶ seconds to 10⁻17⁻18 seconds. Particles that live such short lives are usually called resonances. They cannot be seen like normal particles. They decay so quickly. They are simply observed in processes in a study as some peaks in their energy distribution. There are a lot of hadronic resonances that have been discovered, but they all fall under the classification that I mentioned. They all fall under this scheme, and they all consist of quarks. And knowing the quark structure, we can talk about the properties of these parts. Naturally, the question arises, is there anything new? Are there any new hadrons that we don't know anything about? Here, as the energy increases, as the masses increase, new particles were born. But it turned out that some of them decay so quickly that it simply does not have time to exist in the form of bound states of quarks. Generally speaking, if we say that a particle is made up of something, say a hadron is made up of quarks, it means that these quarks are bound together. It's common to talk about bound states. Now, these bound states may simply not form if they don't have enough energy. And some hadrons actually don't really exist because the bound state doesn't arise. In this sense, it is possible that we have already reached a certain limit at accelerators, beyond which heavy particles will not be formed, because they will decay faster than they form a bound state. We already have such examples. But the properties of hadrons as particles that interact strongly, they are quite well understood. Hadrons have an electric charge, so in addition to strong interactions, they take part in electromagnetic interactions and also decay, and decay is carried out due to the weak interaction, when, as a rule, emitted neutrino. So hadrons are particles that take part in almost all the interactions that we know of. They participate in strong interactions, in electromagnetic interactions, in weak interactions, and in gravitational interactions, which are very weak. The enigmatic term quark, it seems quite incomprehensible. That's exactly what drew him in. Interestingly, the word first appeared in James Joyce's novel Ulysses. There was even a poem titled 3 Quarks for Mr. Mark. The meaning of these quarks was quite unclear, yet I found the word appealing. Then, in the 1960s, scientists were in the process of developing a theory related to elementary particles. At that time, these elementary particles were essentially what we now refer to as baryons or mesons. A typical representative is a proton or neutron, which forms the atomic nucleus. When they were building a theory of these particles, and there were a lot of them at that time, then these quarks became relevant and began to be used. Overall, this scheme was proposed for use by the American physicist Murray Gell-Mann. He is a Nobel Prize winner, a very famous man. And there was a second other man. His name was Zweig. He used another word, aces. He called them aces. Aces didn't catch on. Quark was deemed more appealing. What are quarks? Nature, as we see it now, seems like a nest doll. There are layers. Each time we open one, something new appears. There is an atom, the atomic nucleus, and the nucleus consists of protons and neutrons. Once, these were thought to be elementary particles. Then it was found there are many more such particles. First in the cosmic rays, and then at accelerators, new particles began to be discovered, and their number quickly grew to several dozen. This led to the desire to classify them in some way, to create something akin to the periodic table, with rows and columns where each particle would have its own place. It turned out that such a table could indeed be constructed if one assumed that all these particles are composed of certain fundamental building blocks, essentially, that a nest doll of particle structure goes even deeper. That protons, neutrons, K-mesons, rho-mesons, and so on, those particles we found are composed of even tinier components, which we suggested naming quarks. It was discovered back then that just 3 of these building blocks were sufficient to form all particles. These blocks were named with 3 terms: upper, lower, and strange. These are U, D, and S, standing for the English words up, down, and strange. So how exactly are particles made up of these quarks? Well, it's actually quite straightforward. For example, consider the proton. It consists of 2 U quarks and 1 D quark. This combination of UUD makes up the proton. Now, when it comes to the neutron, we have the UDD combination, which results in the neutron. You might take 3 U's, or maybe 3 D's, or even UUS, or UDD. Essentially, all possible combinations are covered. And it turns out that every known particle can actually be assembled from these 3 quarks. In other words, everything known to us so far can indeed be constructed using these 3 combinations. So, just like that, you could create the entire world of elementary particles from only 3 components. It was amazing. However, it wasn't merely a game of chance. Behind this toy building block was a mathematical structure, difficult to explain, known as group theory. Basically, this theory suggested that all particles should form families. These families could be made up of 3, 8, or 10 particles. It turned out all the elementary particles found by then fit perfectly into these families. We even had some gaps, and when they were filled, it was like this. This particle construction was called the octal way, related to group theory, which I won't explain. Everything was fine until in 1974, I think, a new particle was found that didn't fit this scheme. It didn't. Initially, there was quite a bit of noise and things were hard to understand. And then it became clear that to explain it, we needed to come up with another particle, which was another quark, a fourth quark. It actually turned out to be 4 quarks. So this delightful poem, 3 quarks from Mr. Mark, had to be adjusted slightly, as we had to introduce the 4th quark. Furthermore, it turned out that when physicists attempted to construct a theory that not only described the existence of particles, but also aimed to describe their properties and their interactions. Their mutual transformations, the 3 quarks, turned out to be an unfortunate combination. It turned out that, for example, some decays of particles that, for some reason in nature, do not occur in this theory, on the contrary, were supposed to occur well. And when they analyzed it all, they realized that if there were 4 quarks, if there were an even number of quarks, then everything would work out just as it should. Just these decays would be forbidden, and everything, nature would fit. So the 4th quark had been talked about before, but in 1974, they discovered it. Quarks became 4 and everybody was happy and everything worked fine. But a short time later, they discovered a 5th quark. So they discovered a 5th particle. By the way, the 4th quark was called the charm quark, or C quark. This charmed quark gave birth to the whole physics of charm, or charmed physics. And then they discovered the 5th quark, which was called the B quark, from the word bottom, or from the word beauty. And beautiful physics was born. There were 5 quarks. And again, there was that problem with their transitions of one particle into another. And of course, the road was already blazed. And everybody started saying there must be a 6th. They started looking for the 6th. At the end of the last century, a 6th quark was discovered, named T-top or truth. Thus, there were 6 quarks. Now we say there are 6. When they became 6, it was possible to classify quarks, not just view them as building blocks of particles. A curious property was that these quarks grouped into pairs. The first pair is the U and D quarks, which were there from the start. The second pair consists of the S and C quarks, or more correctly, the C and S quarks. The third pair consists of top and bottom. Interestingly, these pairs of quarks have absolutely identical properties, each and every pair. The only distinguishing factor between them is that each successive pair is heavier than the one before it. Otherwise, they are exactly alike in every way. This led to the idea that, in fact, we are dealing with what was referred to as a generation. Sometimes the term family is used, but generation is the more accurate word. So there are 3 families or generations. The first quarks are the first generation, the second couple is the second, and the third couple is the third. They're identical, just one generation is older than the other. In physics, older means heavier. So, with 3 generations, the question is, why do we need them? What composes the world we see? It's protons and neutrons, just that. There's an electron, but let's focus on quarks. There's a proton and a neutron. Why do you need 2 more quarks? Then 2 more. That mystery persists. The visible world that we see, sit on, walk on, the air we breathe, everything around us, stars, whatever, is made of two quarks. More precisely, it consists of protons and neutrons, which are made of two quarks. By the way, it's very interesting what the properties of these quarks are. Well, let's say a proton has an electric charge. In units of electrons, that charge is +1. The neutron has no charge. A quark, if they form protons and neutrons, must have an electric charge to add up to the right charge. Since the proton is made up of 3 quarks, it is very natural to assume that the electric charge of a quark is a multiple of 1. 1/3. That's our choice. The electric charge of a quark is either 2/3 or -1/3. So the proton, how does that add up? You do 2/3 plus 2/3 minus 1/3 gives you +1. And how do you form a neutron? 2/3 minus 1/3 minus 1/3 results in 0. These are all baryons. And baryons are particles that strongly interact and have a half-integer spin, meaning spin 1/2, 3/2, and so on. These are all baryons, and they consist of 3 quarks. Each quark has a spin of 1/2, so from these 3/2, we derive a half-integer spin of a baryon. Consequently, we always form combinations of 3 quarks. However, mesons possess a spin of 0. Therefore, they are constructed from 2 quarks, with a spin of either +half or -half. For instance, here is the well-known pi meson. The pi meson acts as a nuclear force carrier. It has spin 0, and its charge is +1, -1, or 0. It's composed of 2 quarks. How is this done? Take U or anti-d. I should mention all particles have antiparticles, including quarks. Antiparticles have opposite charges. So, take an anti-d quark. The quark's charge is 2/3, the d quark's -1/3. Accordingly, the anti-d plus 1/3. So 2/3 plus 1/3. That's 1. That makes pi plus meson. And so everything else. This is how all observable elementary particles are built from quarks with fractional charges. Leptons are light, quickly interacting particles. A well-known lepton is the electron, a particle discovered over 100 years ago. It's the same particle that flows in wires when an electric current is present. It turns out that the electron isn't the only particle in the lepton family. Shortly after the electron, another particle was found, named the muon. It turned out that it was almost an exact replica of the electron, except that it is 200 times heavier. Generally speaking, the electron is the lightest charged lepton we know. If we measure its mass using units accepted in the field of elementary particle physics, which are energy units, according to Einstein's formula, rest energy equals mass times the speed of light squared. Therefore, mass is typically measured using energy units. The mass of an electron is equivalent to 500,000 electron volts. And muon is 200 times heavier. The next discovered lepton is the tau lepton, even heavier. All 3 charged particles are almost identical, sharing properties in electric charges, differing only in mass. However, these 3 don't complete the lepton family. During the process of decay, another elusive particle is created along with the electrons. Initially, it was not clear where the missing energy went. Then Pauli suggested that this energy is carried away by a neutral and light particle. Fermi proposed to name this particle neutrino, which means a small neutron. This is how the neutrino became part of physics. The neutrino possesses a very small mass and lacks any electric charge. It does not participate in strong interactions, making it extremely difficult to detect. However, it originates in weak interactions. So, along with an electron neutrino is created. And what accompanies a muon? A neutrino is also created. Initially, these 2 particles were thought to be identical, but later it was discovered they were distinct. It was then concluded that each lepton likely pairs with its partner, an electron with an electron neutrino, muon with muon neutrino, and tau with tau neutrino. By the way, the tau neutrino was discovered in the year 2000, and it's the last particle from the standard model that we know of, which was discovered in the last century. So, by doing this, we obtain a total of 6 leptons, consisting of 3 charged leptons and 3 neutral leptons. Each of these leptons satisfies the same equation, which is commonly referred to as the Dirac equation, and it is satisfied by particles that have a spin 1/2. Quarks, as particles with spin 1/2, also satisfy the Dirac equation. But with neutrino, the story is more complicated. Neutrino has no electric charge. And if a particle has no electric charge, then it could satisfy another equation. And there is such an equation. It's called the Majorana equation, in honor of the Italian physicist Ettore Majorana. So, what is the equation that neutrino satisfies? Is it Dirac's or Majorana's? Or, to phrase it differently, is a neutrino a Dirac particle or a Majorana particle? What distinguishes the two? The key difference is that if a particle is Majorana, it is its own antiparticle. This implies that when two such particles encounter each other in the universe, they can annihilate each other. On the other hand, if it's a direct particle, this annihilation process is impossible. To truly understand how the neutrino is structured and which equation it follows, we must perform an experiment and examine if there is a mutual annihilation between two neutrinos. Currently, an experiment is underway known as neutrinoless double beta decay, and up to now the outcome is that we are unable to determine if the neutrino is Dirac or Majorana. It's likely that we will uncover the answer to this enigma in the future. What else is fascinating about neutrinos besides this? It's the fact that all quarks, leptons, and other particles transition into one another during interactions. Quarks of one type transform into quarks of a different type, and leptons of one type transform into leptons of another type. These are processes that we can observe. However, the neutrino is a unique particle. The key point is that this transition of particles from one type to another generally happens at distances that are virtually impossible to detect experimentally. Yet, when the particle is extremely light, and the neutrino is assumed to be very light, these distances become significant and can extend to macroscopic scales, such as meters or even kilometers. It turns out that there is a phenomenon commonly referred to as oscillation, which occurs when a neutrino travels through a medium. Initially, we observe one type of neutrino, but after it travels some distance, for instance, from a reactor where the neutrino originates, we notice that the number of this particular type of neutrino diminishes. Meanwhile, a different type of neutrino starts to appear. This behavior is described by the Syn function, the Syn law. That is, there is such an oscillation of one variety of neutrino and another variety of neutrino. This effect is called the effect of neutrino oscillations. I've already said that with other particles we do not observe this because the distances where oscillations occur are completely microscopic. They're inversely proportional to the mass. And in this case, the mass is very small, so the distances are large. So these neutrino oscillations have been experimentally detected. It should be said that the transition of particles of one kind into another is impossible if the particles are massless. It only happens when the particles have mass. Therefore, the neutrino oscillations tell us unequivocally that neutrinos are massive particles, although the mass of this is extremely small. Interestingly, we still don't know what that mass is, because neutrino oscillations confirm the very fact that there is this mass and only allow us to measure the difference in mass between different neutrinos, but do not allow us to measure the absolute mass scale. So, the mass of the neutrinos is still a mystery. We hope that other experiments, which are already sensitive to the mass itself, will help us answer this question. Experiments searching for neutrinos are always very challenging. This is because a neutral particle has almost no interaction with the medium. The neutrinos that come from the sun penetrate the Earth, and we do not feel them at all. because their interaction is extremely weak. We are almost transparent to neutrinos, which makes it extremely challenging to detect the interaction of these particles. For this reason, detectors need to be enormous in volume to boost the likelihood of neutrinos interacting with any particles within this vast space. It's for this very reason that underground laboratories are established. They are located underground because it's necessary to shield the experiments from cosmic background radiation, those particles that reach us from outer space. Thus, the cleaner a laboratory is, the higher the chances we have of detecting events that are of interest to us. Therefore, in these underground laboratories, they are constructing large facilities with the aim of capturing neutrino signals. For instance, there's the Super Kemiokende laboratory situated in a salt mine near the Japanese village of Kemioko. This lab resembles a barrel standing 40 meters tall and 15 meters wide, filled with the purest water, and its walls are entirely covered with photomultipliers. Any signal that occurs within this massive volume will be transmitted through photomultiplier tubes to the detecting device. These instruments, roughly the size of a building, are made underground to detect neutrinos. So what exactly did they detect? Well, it turns out to be quite fascinating. First of all, it detects the neutrino signal that is coming to us from the sun. For a long time it was a mystery because, according to the models of the sun, a certain amount of electron neutrinos was expected to reach us. And we're getting far fewer of them. We thought there must be something wrong with our understanding. And then the mystery was solved. It turned out that the phenomenon of neutrino oscillations explained everything. Part of the neutrinos that fly to us from the sun, electron neutrinos, turns into muon neutrinos, so the number of electron neutrinos is less. This is how the phenomenon of solar neutrinos oscillations was explained. However, there are other types of neutrinos. Some neutrinos come to us from cosmic rays, and these are usually muon neutrinos. Interestingly, these muon neutrinos also appear to be fewer than anticipated. Once more, the phenomenon of oscillation helped us understand why the quantity of muon neutrinos didn't match our original expectations. There are several sources of neutrinos, which include solar, cosmic, and those originating from nuclear reactors. Neutrinos are categorized into three distinct types: electron, muon, and tau neutrinos. These particles have the ability to oscillate and mix among themselves, which means they change from one type to another. To fully understand and analyze them, it's necessary to untangle them. This complex process is achieved by utilizing three specific angles that help in differentiating and studying their behavior. Well, like the typical rotation angles. Now, these three angles have been measured experimentally. It turned out that all experiments on solar, atmospheric, and reactor neutrinos are accurately described by the standard model with a specific rotation matrix. This matrix was named the Pontecorvo-Maki-Nakagawa-Sakata matrix. It includes one Italian physicist, Bruno Pontecorvo, who worked in the Soviet Union, and three Japanese physicists. In the quark sector, there is also such a matrix. It is usually called the Kabibo-Kobayashi-Maskawa matrix. Also, one Italian physicist and two Japanese physicists. The analogy between the quark and lepton sectors showed up here as well. There is mixing of flavors, as it is commonly said, in the quark sector, and exactly the same mixing of flavors in the lepton sector. These two mixing matrices explain all transitions of quarks, or leptons of one sort in a quark, or lepton of another sort, and in particular explain all phenomena of neutrino oscillations. Now, all these angles are well measured, all consistent with expectations. And there's still one little mystery left, and that's the phase that's in this matrix. Well, if anyone knows what a complex number is, a complex number has a modulus and a phase, so the phase that is in this matrix is still not very well known, although it is also an experimentally measurable quantity. Thus, the picture that emerges looks like this. We have three generations of quarks and three generations of leptons. The first generation includes the top and bottom quarks, along with the electron and electron neutrinos. The second generation consists of the charm quark, the strange quark, the muon, and the muon neutrinos. And the third generation is made up of the top quark, bottom quark, tau, and tau neutrinos. That's 3 generations. It's such a complete analogy between leptons and quarks. I just wonder what these 3 generations are meant for. This is a mystery that has yet to be answered. But here, the 3 generations of quarks and leptons represent the basis of the modern model of elementary particles. It should be said that the neutrino, which is present in the lepton sector, plays a very important role in cosmology. The point is that neutrino is a stable particle. And as a stable particle, well, it simply has nothing to decay into. There is no lighter particle. It has existed since it was born in the early universe. Both the properties of the early universe and in general the properties of the modern universe depend very much on how many varieties of neutrino are present in this universe. So the distribution of heavy elements in the universe, the microwave background of the universe, and many other facts indicate that the number of neutrinos in all probability is equal to 3. It means that the number of generations is equal to 3 if we talk about quark-lepton symmetry and talk about generations. However, there is still a small catch. It is possible that in addition to the 3 generations, there are also neutrinos, which do not participate in any interactions, neither in the electromagnetic, nor in the strong, nor in the weak. Such neutrinos are called sterile. Here is an experimental window for sterile neutrinos still remains. Perhaps the next experiments will allow us to answer the question of whether there are sterile neutrinos or no sterile neutrinos. If there isn't, then the analogy between quarks and leptons is considered complete. However, if there is, then the neutrino still offers us new and intriguing mysteries to solve. Symmetry. It turns out that this is indeed the most crucial concept in the field of particle physics. From a mathematical perspective, the core of elementary particle physics is fundamentally the theory of symmetry. On the other hand, the concept of symmetry in everyday life should be quite familiar to everyone. In general, symmetry refers to some form of similarity or invariance of an object or phenomenon when it undergoes a transformation. Well, for example, the human body. Here we're looking at a human being. It's symmetrical with respect to reflection with respect to the axis that goes through the center of the body. The left side of the body and the right side of the body are the same. Here is symmetry, the simplest symmetry of reflection. But we know that the heart is on the left. So the symmetry is not complete, so it is only visible. But nevertheless, if we don't talk about the inside of a human being, it is an example of symmetry. Here's another example. Consider a snowflake. Snowflakes are very beautiful. They're hexagonal or octahedral. They always show beautiful symmetry. What is symmetry? If you rotate a snowflake, it remains unchanged, but it must be rotated at a specific angle to align with itself. So there's an invariance group with the snowflake. These are the invariance groups that appear everywhere in physics. Furthermore, when we strictly define the concept of symmetry, it refers to the invariance of something under certain transformations. For example, with the human body, we talk about reflection concerning the axis, while for a snowflake, we discuss rotation around an axis. Interestingly, all transformations can actually be classified, a process known as group theory. And these different groups hold a very significant role in the field of particle physics. Transformations can occur in a continuous manner, allowing for any parameter, or they can be discrete, such as rotating by a specific angle. For example, when you rotate by angles like pi over 2, pi over 3, or pi over 6, these are considered discrete transformations. Another example is reflecting the human body, as it involves switching the left side with the right side. When we gaze into a mirror and see a reflection, it represents a reflection transformation. Interestingly, when you look in the mirror, the left hand appears as the right hand and the right hand appears as the left. If there is complete sameness, then the mirror world aligns perfectly with our own world. However, if our hands differ, our worlds do not align. For instance, in the mirror, a person's heart appears on the opposite side. Thus, we lack complete symmetry with the mirror world. All of this is evident in particle physics too. When we discuss discrete transformations, the most well-known transformation is the reflection of space. which involves altering the direction of space. The theories that describe the physics of elementary particles generally exhibit invariance, meaning they remain unchanged with respect to space reflection. Additionally, there is a transformation involving the mapping of time. We understand that in our daily lives, time cannot be reversed. Time flows in just one direction. However, particle physics can be different. It's typically formulated so that time can actually be reversed. Another transformation involves changing the sign of the electric charge. Here, we change the signs of the electric charges for all particles. Electrons will have a positive charge, protons a negative charge, and so forth. The question is, will the world change or not? Some elements from the world will not change, and some will change. This is also symmetry. It is not exact. There is a continuous symmetry. Well, from quantum mechanics, we know that there is a so-called wave function. It is a complex number. It has modules phase. It turns out that the phase can be continuously changed. And in this case, the values of the observable will not change. So there is a symmetry with respect to the phase measurement. The phase can be adjusted in a continuous manner. This is known as continuous symmetry or phase symmetry. Interestingly, there are conservation laws linked to every form of symmetry. If there's symmetry, something must be conserved. For example, phase symmetry results in the conservation of electric charge. Although it seems like an abstract transformation, it actually explains why electric charge remains conserved. There are additional examples. Essentially, if you identify symmetry, you can uncover various properties of the theory, or vice versa. We should formulate the theory in such a way that it possesses a certain symmetry. Then the principles we put into it will be observed. The principles that underlie the special theory of relativity are related to the invariance of physical phenomena when changing the reference frame. We must build into the theory a symmetry with respect to changes in the reference frame. This is usually called Lorentz invariance. That is, it is a symmetry that changes the reference frame or changes the coordinates in space. It turns out that the construction of any particle physics must have a large number of all kinds of symmetries, and it very much limits the construction of the theory and at the same time tells us how to construct the theory correctly. As the study of elementary particle physics advanced, we found many new symmetries that were previously unknown. For instance, quarks have a fascinating property. It was discovered that quarks, which make up hadrons, are fermions and thus cannot occupy the same ground state with identical energy. Rearranging them alters the wave function sign, and if they are completely identical, the wave function will be equal to 0, and there will be no hadron. This problem was solved by the introduction of so-called color of quarks. Color is a conditional concept you could take anywhere, and postulated a symmetry regarding the fact that you can change color continuously in any way you want. This symmetry finds mathematical embodiment in the form of the so-called special unitary group with 3 colors. And so the theory of quarks is built so that it was invariant with respect to this very group. It turns out that symmetry not only results in charge conservation, but with quarks, it also conserves color charge. It also defines the interactions between these particles. The modern theory of unitary particles is essentially symmetry theory. It's often stated that the standard model is based on 3 symmetry groups, which are quite similar to each other. They are special unitary groups. This is the group referred to as SU3, SU2, and U1. That's the way they're labeled in mathematics. Therefore, any theoretical framework must adhere to certain symmetries. When discussing the modern theory of elementary particles, besides these 3 symmetry groups I mentioned, there are also discrete symmetries, which I have also mentioned. These include time reflection and space reflection. Additionally, there's the replacement of a particle with its antiparticle, and there is also Lorentz invariance, which refers to invariance with respect to the change of the reference frame. Here is the modern theory of elementary particles, which possesses all these symmetries. As mentioned, symmetry not only determines the particles, but also their interactions. It turns out that phase symmetry, which ensures the conservation of electric charge, also leads to the emergence of the photon, or ordinary light, a carrier of electromagnetic interactions. But say the presence of color symmetry of quarks leads to the fact that there are special particles that are carriers of strong quark interactions. These particles are called gluons, from the word glue. That is, symmetry in fact determines the entire physics of elementary particles. Sometimes it is even said that it doesn't matter how you formulate a theory. The main thing is what symmetry this theory has. Symmetries can be inexact. This is a very interesting situation where the symmetry is broken a little bit. Here again is a complete analogy with the human body. There is kind of left-right symmetry, but one eye may squint a little bit, or one ear may be a little bit different than the other. And the left-right symmetry is broken a little bit. Here in particle physics, the same situation exists. Some symmetries are broken. For instance, consider that the symmetry of space and time reflection remains intact in electromagnetic and strong interactions, but weak interactions disrupt this symmetry. Spatial symmetry is typically denoted by the letter P, while asymmetry in time reflection is represented by the letter T. Asymmetry in swapping a particle with an antiparticle is indicated by the letter C. Moreover, there exists a theorem known as the SPT theorem, which states that the theory of elementary particles must remain invariant under SPTT transformations. It was discovered that strong electromagnetic interactions are indeed invariant with respect to each of these transformations individually, yet weak interactions do not share this property. Initially, it was understood that parity, meaning the reflection of spatial symmetries, is not preserved. Then it was discovered that the charge symmetry is actually not preserved. This led to the introduction of the notion of combined symmetry, which occurs when we replace space with its reflection and also replace a particle with its corresponding antiparticle. Feynman, in his lectures, even has this wonderful phrase stating that the positron is an antiparticle to the electron. It is essentially an electron that moves backwards in time. And that's really true. However, later on, it was found that this symmetry is also broken. It's fascinating in particle physics that weak interactions break this combined symmetry. Only the combination of all three symmetries, Cp and T, remains unbroken. Another instance of broken symmetry is that any symmetry implies particles responsible for interactions must have zero mass. The photon having zero mass shows the symmetry isn't broken. The rho has no mass, meaning the symmetry remains intact. However, in weak interactions, the particles responsible for these interactions are known as intermediate vector bosons. These particles are not massless. This implies that the symmetry is broken. This is an entirely different and intriguing subject about how the symmetry in particle physics is broken, specifically in weak interactions. It's commonly referred to as spontaneous symmetry breaking. In other words, symmetries can indeed be broken, meaning they can be imperfect or inexact symmetries. Even when a symmetry is broken, a portion of it still persists and actually influences the configuration of the entire body. Curiously, defining what symmetry truly is can sometimes be more challenging than discovering a particle, as this symmetry is not always easy to identify. It's not surprising that the achievements in hadron physics and the categorization of hadrons were due to the discovery of a symmetry, which was subsequently named the SU3 symmetry that allowed to classify all particles. The modern advancement of particle physics is linked to new symmetries. On one hand, there's symmetry between quarks and leptons, likely represented by a mathematical formula yet to be discovered. On the other hand, new symmetry ideas have emerged, like symmetry between whole and half-spin particles, known as bosons and fermions. Here's the symmetry between bosons and fermions. This kind of symmetry is called supersymmetry. If a theory has supersymmetry, it means that every boson in the theory has its partner, a fermion, in much the same way that an electron has a neutrino as its partner. And here it is related to the SU2 group, and here the electron must have some scalar particle as its partner. Such particles have not been found in nature yet. So whether this is a symmetry, the correct symmetry of nature or not, is unknown. However, this is currently the focus of the most intensive search and, in a sense, represents the top priority task of modern colliders. From high school physics, we encounter the concept of force. There are various types of forces. There is the force of attraction, the force of friction, the force of rolling, and the force of elasticity. There are numerous forces. It should be noted that not all of these forces are fundamental. Often, many of these forces are actually secondary phenomena. For instance, the force of friction is considered a secondary phenomenon. It's essentially the result of the interaction between molecules. Moreover, even the interaction of molecules can be seen as a secondary effect. In molecular physics, for example, there are the van der Waals forces. These forces arise as a secondary consequence of electromagnetic interactions. Our goal is to understand the fundamental force itself. What are the fundamental forces in nature that dictate everything, from which all these secondary forces are derived? However, electromagnetic forces, or electric forces, are considered fundamental interactions as we currently understand them. For instance, Coulomb's law, which is familiar from school physics, is regarded as a fundamental law. Yet it doesn't stand alone in its generalization. It actually derives from Maxwell's equations. These equations comprehensively describe all electric and magnetic forces found in nature. Therefore, electromagnetic interactions are indeed the fundamental forces of nature. Another example of a fundamental force in nature is gravitation. As learned in school, Newton's law of universal gravitation is well known, but it has now been generalized in Einstein's equation. We now refer to it as Einstein's theory of gravitation. Gravitational forces represent fundamental interactions in nature. At one time, it seemed that only these two fundamental forces were in existence. However, we later realized that this is not the case. Specifically, when the atomic nucleus was discovered, there was a challenge to comprehend why particles stayed inside the nucleus instead of flying apart. This led to the introduction of the concept of nuclear forces. These forces were measured, understood, and described thoroughly. However, it was later discovered that they are not fundamental. Nuclear forces, in a certain sense, are similar to van der Waals forces. The truly fundamental forces responsible for strong interaction are the forces between quarks. Quarks interact with each other, and as a secondary effect, protons and neutrons in the nucleus interact with each other. The fundamental interaction is the interaction of quarks by the exchange of so-called gluons. So this is the third fundamental force in nature. But the story doesn't end here either. It turns out that particle decays. And particles decay, or heavy particles decay into lighter particles. The decay of elementary particles is explained by a new interaction known as the weak interaction. It's termed weak because its forces are significantly weaker than electromagnetic forces. However, it turned out that the theory of the weak interaction, which initially existed and described all decays quite well, did not function effectively as energy increased. It was eventually replaced by a new theory of the weak interaction. This new theory turned out to be entirely universal and was constructed on the same principle as all other interactions. In the modern world, there are 4 fundamental interactions. I'll tell you about the 5th one too. So these 4 fundamental interactions, electromagnetic, strong, weak, and gravitational interactions, are based on one principle. The principle is this: the force between particles arises from the exchange of some intermediary, the carrier of the interaction. Electromagnetic interaction is based on the exchange of a quantum of light or a quantum of electromagnetic waves. This is the photon. Photon is massless particle. Charged particles exchange it, and due to this exchange there is interaction between particles, forces between particles. Coulomb's law describes it that way too. The other interaction is the strong one. There is also a carrier particle there, and there are also particles that quarks exchange. These particles are called gluons. There are 8 of them. They are also massless particles. The third interaction is the weak interaction, and here too the intermediary is the particles called intermediate vector bosons. And these particles, there are 3 of them, and they are massive, meaning they are quite heavy. This mass, the heaviness of these particles, explains why the weak interaction is so weak. The fourth interaction is gravitational, and it occurs by exchanging a quantum of gravitational field, which is called a graviton. It should be noted that this graviton has not been experimentally detected yet. Quantum gravity is something we do not quite feel and do not fully know how to describe. So all interactions are the act of exchanging some particles. Here we come back to the notion of symmetry. All such interactions involve symmetry. Symmetry tells us how many such particles there are and how much mass they have. If the symmetry is exact, the mass is 0. A photon has mass 0, a gluon has mass 0. If the symmetry is broken, the mass is not 0. Intermediate vector bosons don't have 0 mass. The symmetry is broken there. Gravitational symmetry remains unbroken, and the graviton indeed has 0 mass. There exist 4 fundamental interactions, which actually explain everything observable. All other forces are merely secondary effects of these interactions. However, in the year 2012, a new particle was discovered that gained significant fame, known as the Higgs boson. The Higgs boson also acts as a carrier of interactions between quarks as well as between leptons. So now perhaps it is appropriate to say that there exists a fifth force, and the carrier of this force is the Higgs boson. Here too the symmetry is broken, as the Higgs boson is a massive particle. Thus the number of fundamental interactions, and in particle physics, we usually prefer the term interaction rather than force, has now reached 5. Could there be new interactions? We don't actually know that for certain. In the standard model of particle physics, there are no other interactions. There are only these 5 known interactions. However, it is possible that the model we are currently considering, which so accurately describes all the experimental data and all the phenomena we observe in the world around us, might not be entirely complete. If that is the case, then potentially some new forces and new interactions could emerge. Well, for instance, if there happen to be these so-called supersymmetric particles, meaning if there's a new kind of symmetry in nature, then this new symmetry will bring about the emergence of new particles that act as mediators between other particles. As a result, a new fundamental force in nature could emerge. Therefore, this possibility is still present. It's quite interesting to note that every new interaction invariably leads to some new phenomenon. Let's say if there were no weak interaction, decay wouldn't occur. Without decay, nuclear reactions wouldn't happen. Without nuclear reactions, the sun wouldn't shine. Without the sun's light, there'd be no life on Earth. So, this interaction's presence is vital to us. Without strong interaction, there'd be no stable atomic nuclei. Without nuclei, there'd be no atoms. There would be no atoms, and consequently, there would be no us. So, it turns out that all forces are somehow necessary in a general sense. Well, there's the electromagnetic interaction. We receive our energy from the sun. These are rays of light that reach us from the sun, which is electromagnetic interaction. And without it, the Earth would be cold and uninhabitable. It turns out that all the interactions we know are necessary for something. The Higgs interaction with the Higgs basis is what provides the mass of the particles. The fundamental particles gain mass by interacting with the Higgs field. You can't live without it either. But I'm not talking about gravitational interactions which fly off the surface of the planet. That is, it turned out that all the interactions that exist in nature that are now discovered, they are all vital for everything that we understand and know, and we ourselves all exist. But what if there was a new interaction yet to be discovered? Here's another example. The proton in the nucleus is stable, which is crucial for life. Experimentally, the proton's lifetime is limited to 10 to the 34th power of years. This implies there's no rule against proton decay, but it needs a new force and interaction. There are several theories that predict the decay of protons. They propose a higher symmetry group and introduce new interactions that are currently unknown to us. Is this true? For now, this remains a question for experimental investigation. So, as I mentioned, all fundamental interactions are currently constructed upon a single underlying principle. In this context, there is indeed a certain unity to nature. Occasionally, the question arises about whether it is possible to explain the number of interactions that exist in nature, as if to grasp the reason behind why there are 4 interactions or why there are 5, and there may be more. There are various theories of how the existence of a certain number of fundamental interactions could be explained. These theories are often called grand unification theories. These theories combine different kinds of interactions into one. This is reminiscent of a tree growing. There is a single trunk, and then it branches further, and different branches are obtained. The idea is approximately the same, that there is a single root of all interactions, as if a single trunk, and then as a result of symmetry breaking, this trunk begins to branch and several fundamental interactions are formed, which we experimentally observe. Verification of this hypothesis requires physics at very high energies that are inaccessible to modern experiment, and probably will never be accessible. However, we are able to find a way around this issue. After all, we have an accelerator, and naturally, that's the universe. Some processes occurring in the universe allow us to test these bold hypotheses that suggest there might be a single root for all interactions. Additionally, another intriguing challenge in understanding the interaction in nature is figuring out how gravity connects to all the other interactions. Gravity, in a way, stands somewhat apart from them. While the principles of the theory are quite similar, in his era, Einstein attempted to construct a unified theory that combined gravity and electromagnetism. At that time, it appeared quite feasible, yet it never materialized. Today, we have gained a bit more knowledge. We understand that there's not only a strong interaction, but also a weak interaction. Thus, if we were to construct a unified theory now, it seems we should incorporate all these additional interactions together. But nevertheless, such a unified theory has not yet been created, and so far we have not been able to unify gravity with the rest of the interactions. All interactions except gravity obey the laws of quantum physics. This is quantum theory. All particles are quanta of a particular field. Quantum gravity doesn't exist yet. We can't create it yet. What's the reason? What are we doing wrong? What don't we understand yet? It's all still quite a mystery. However, the number of fundamental interactions that have already been discovered strongly suggests that there is likely some kind of unified scheme. Symmetry plays a crucial and very important role in the field of particle physics. We use symmetry not only to categorize particles, but we also use symmetry to predict what kinds of interactions exist. The fact remains that the known carriers of all types of interactions, whether strong, weak, or electromagnetic, are particles that are dictated by the rules of symmetry. They are also sometimes called gauge fields. This is because the symmetry groups of elementary particle physics are called gauge groups. These are groups that depend on a space-time point, or, as it is sometimes called, local symmetry. So, these local symmetries, in fact, determine the whole appearance of the theory of elementary particles. Simultaneously, symmetries can occasionally be found to be inaccurate or, as we sometimes describe them, broken. What exactly does this imply? It implies that there are certain interactions or particular summands included within the model that lack the symmetry property, or the symmetry itself is broken. Generally, violations of symmetry can occur in 2 different ways. This issue is not limited to just elementary particle physics. There exists what we call explicit symmetry breaking, which occurs when something distinctly deviates from symmetry properties. And there are times when the whole system remains symmetric. If something is described by equations, the equations may turn out to be symmetrical, or just the appearance turns out to be symmetric. And some initial or boundary conditions do not possess this symmetry. In such a case, it is customary to speak of spontaneously broken symmetry. What does it mean more precisely? Let us consider such an example. Consider a bottle with a convex bottom. If this bottle is placed standing vertically on the table, it exhibits rotational symmetry concerning the axis that passes through its center. When you rotate a bottle around this axis, nothing appears to change. Now, let's imagine you tilt the bottle just a little bit. In this case, the symmetry is disrupted. Now, consider if we were to throw a pea inside the bottle. While the bottle was in its upright position, the pea would hit the bottom of the bottle, and we wouldn't be able to tell exactly where it would land, because every spot on the bottom of the bottle looks exactly the same. When we talk about potential energy, the energy is the same, and the pea can drop to any position. So what we did was tilt the bottle. This action immediately breaks the symmetry, and naturally the pea will fall to the spot where the energy is the lowest. Now imagine we return the bottle to its original position. The symmetry is restored, but the pea is already resting in a specific spot. It's the very position of this pea that disrupts the symmetry. Here we have an instance of spontaneous symmetry breaking, where the entire system remains symmetric, yet the initial position of the pea disrupts the symmetry. Let's consider another example. Imagine we have a magnet located on a horizontal plane, where all positions within the magnet are identical. We discuss symmetry in terms of isotropy, as well as regarding shifts or rotations within the plane. Well, let's say we apply a magnetic field. Domains with a distinct magnetic field form inside the magnet, like the poles aligned with the field. The symmetry is broken, and the magnet is inhomogeneous. If we then turn off the magnetic field, the domains stay. So, even in a symmetric situation, conditions arise that break the symmetry. This is another example of spontaneous symmetry breaking. So, it would seem, what does all this have to do with particle physics, especially the bottle? Well, it turns out it has everything to do with particle physics. The thing is, there was a problem in particle physics. The problem had to do with the masses of all the particles. Exact symmetry usually says that particles are massless because mass terms, or masses, if you introduce them into the theory, they break the symmetry. The photon, say, is a massless particle. The fact that the photon is a massless particle is a consequence of the phase symmetry of quantum electrodynamics. Gluon, a particle of strong interactions, is also a massless particle. It is a consequence of the symmetry of strong interactions. And in weak interactions, if the symmetry was exact, also carriers of weak interactions would be massless. But we know that these carriers, they are called intermediate vector bosons, W and Z. They are very massive. They have a very large mass, about 100 times the mass of a proton. Here it turns out that symmetry forbids mass to these particles, and the particles have mass. It would seem that one could then abandon symmetry, but the property of symmetry and weak interactions is experimentally very well tested and established, and in fact from the experimental data, this symmetry was born. Then it is asked, how to solve this contradiction? On the one hand, particles have mass, and on the other hand, symmetry forbids this mass, and symmetry is correct. The solution was found by using a mechanism called the spontaneous symmetry breaking method. For this purpose, some scalar field is introduced, which has a potential exactly resembling in shape the very bottle I have been talking about. Sometimes it is also customary to speak of a potential in the shape of a Mexican hat, which is about the same thing. You examine this potential, you'll notice that it remains unchanged when rotated around the center. Similar to the bottom of a bottle, the potential has its lowest state, which is degenerate concerning rotations, allowing the minimum to be located at any point. However, when we assign a classical value to the field, or as we refer to it in particle physics, provide it with a mean value or a vacuum mean value, it becomes akin to being positioned at the rim of this bottle, or potential has selected a specific position. This particular position instantly breaks the symmetry. However, the entire potential, the entire theory, and all the equations still remain symmetric. So this is an example of spontaneous symmetry breaking. What does it provide us? Well, it provides us with this. It turns out that if we assume that the field, which is a quantum object, has a classical component that is constant and equal to just this very mean value, then it becomes possible to perform a simple shift operation. We will assume that the field consists of both the classical part and the quantum part. This is how we incorporate it into our equation. It turns out that gauge vector bosons, which are the carriers of weak interactions, will gain mass. This mass will be directly proportional to the average value of the classical field that we have introduced. Furthermore, it turns out that not just the carriers of weak interactions require such assistance. It turned out that neither quarks nor leptons could possess masses if the symmetry remained unbroken. This is due to the fact that the theory of weak interactions is asymmetric between left and right. In other words, if you swap left with right, the theory is altered. This situation does not occur in electrodynamics, nor does it occur in strong interactions. Therefore, in electrodynamics and strong interactions, electrons or quarks can indeed have mass without violating any symmetry. But both quarks and leptons participate in weak interactions, so it is required to introduce a mass term, which is invariant with respect to weak interactions, but it is forbidden. And it turns out that the introduction of the very field I mentioned, which due to its mean value provided mass to W and Z bosons, the same field provides mass to quarks and leptons, and all of them acquire mass proportional to the mean value of this field. This concept of spontaneous symmetry breaking was initially suggested not for particle physics, but for statistical physics. However, it was later adapted to particle physics, providing a method to assign mass to all particles while preserving the symmetry of the equations. Yet, there was a complication. This complication arises because, as demonstrated, it is a theorem that if one performs such spontaneous symmetry breaking, assigning a non-zero average value to the field, then in theory, it inevitably leads to complications. A state with no mass emerges. In the field of particle physics, this is known as Goldstone's theorem, and these states without mass are named Goldstone bosons, after the physicist Goldstone, who proposed the idea. In the realm of statistical mechanics, Bogoliubov addressed this concept and demonstrated the related theorem showing that massless states do indeed arise. This is essentially the same phenomenon observed in both particle physics and statistical mechanics. So, what happened is that scientists, by solving one issue and giving mass to particles through spontaneous symmetry breaking, ended up creating another issue. We introduced these massless Goldstone states, which aren't found in nature. So, how do we address this new issue? It turns out that we can solve two problems at once. It was discovered that there is a mechanism which was even named after the creators of this mechanism. This is known as the Brout-Englert-Higgs mechanism, which demonstrated that the massless Goldstone bosons link with the vector W and Z bosons, creating a massive particle together. Consequently, there are no entirely massless states within the spectrum. Remember that initially W and Z were without mass, and the Goldstone bosons were also massless. Only when unified do they vanish, resulting in single massive vector particles with 3 degrees of freedom, the W and Z bosons. This mechanism was experimentally confirmed when the particle was discovered, now known as the Higgs boson, named after Higgs, who predicted it in his work. However, the mechanism itself, let me emphasize, is named after the 3 authors, Brout, Englert, and Higgs, who independently proposed it in their respective papers. Thus, the mechanism of spontaneous symmetry breaking in particle physics is applied to produce all particles, which are the carriers of weak interactions such as W and Z bosons, along with quarks and leptons, meaning all the Particles that participate in weak interactions have acquired mass. Since at spontaneous symmetry breaking, not all symmetries are broken, but only the group of weak interactions is broken. The particles participating in weak interactions, respectively, acquire mass. Those particles which do not participate in weak interactions do not acquire mass. Here, a photon remains massless. Gluon also remains massless. In fact, the issue that emerged in particle physics was effectively and safely resolved. The remaining task was to secure its confirmation through the discovery of the Higgs boson, which indeed took place in 2012. Consequently, the mechanism of spontaneous symmetry breaking, as a process for the formation of masses or of fundamental particles, was experimentally verified. It is important to note, however, that when we refer to the masses of particles, we are specifically talking about W and Z bosons, quarks, and leptons. We don't mean particles that are made up of quarks, namely hadrons. Here, for example, the proton is made up of 2 U quarks and 1 D quark. The mass of the proton does not result from this mechanism. As a result of this mechanism, the mass of the constituent particles, quarks, is obtained, and the mass of the constituent particles is formed from the total mass of the constituents plus the binding energy. In this sense, our world consists of massive particles, most of whose mass consists of the binding energy due to strong interactions. However, the primary components, which are quarks and leptons, obtain their mass through a process known as spontaneous symmetry breaking. The final third of the 20th century was notable for the development of the standard model of fundamental interactions. This model was not only created but also confirmed through experimental evidence, widely accepted within the scientific community, and eventually honored with a Nobel Prize. So, what exactly is this model? To begin with, it is a comprehensive model that explains the fundamental particles that constitute matter, along with all of their interactions. This model is a quantum field theory model, formulated as a Lagrangian. The theory known as the quantum mechanics of fields describes the quanta as elementary particles, and it encompasses all fundamental particles of matter. There are not many of these particles. They consist of 6 quarks and 6 leptons. These particles engage in 3 types of fundamental interactions: strong, weak, and electromagnetic. In this context, we disregard gravitational interaction because it is negligible and not part of the standard model. So there are 3 types of interactions among 6 types of particles. The standard model has a framework. This framework is often linked with symmetry groups. 3 interactions, 3 symmetry groups. These groups all fall into the same category known as unitary groups. Electromagnetic interactions are explained by the symmetry group U1, a unitary group with 1 parameter. Therefore, the photon is a single particle that carries electromagnetic interactions. The weak interactions are governed by a symmetry group known as SU2. In this case, there are 3 parameters, which means there are 3 carrier particles for weak interactions. These particles are the W and Z bosons. When it comes to strong interactions, they are described by the symmetry group SU3. In this case, there are 8 parameters, resulting in 8 fields of interaction carriers. These carriers are known as gluons. This explanation pertains to the carriers of interactions. Additionally, the matter particles themselves are part of the representations of these symmetry groups. When considering the group of strong interactions, these interactions involve only quarks. Quarks are represented in the standard model as triplets. This means they have quantum numbers that come in 3 distinct values, often referred to using the term color: blue, red, and green, for example. In the context of weak interactions, all particles are represented as doublets. This representation is also the smallest or lowest representation of the symmetry group associated with weak interactions. We have pairs such as top and bottom quarks, as well as the electron and neutrino. Here are some examples of the 2 doublets. Interestingly enough, quarks and leptons tend to repeat each other. This phenomenon is known as generation. There exists a first generation, a second generation, and also a third generation within the standard model. Generally speaking, it's not entirely clear why nature decided on 3 generations. There's the first generation of particles, which make up the whole observable world. Then there's the second generation, which is like a copy. And finally, there's a third copy, known as the third generation. The standard model consists of 3 generations. These particles are fundamental since no structure is observed in them. In truth, we can't make an absolute statement because, for example, the proton once appeared structureless until its structure was found. Thus, we can't claim that particles we now see as structureless will remain so forever. Maybe in the future, something will be uncovered that is currently unknown to us. However, for the time being, the particles that constitute the standard model are particles without structure, highly precise particles. These include quarks and leptons, as I mentioned earlier. And they are depicted as precise particles within the framework of the standard model. When we aim to describe a certain process occurring in nature, generally speaking, these processes do not involve the quarks directly. Instead, they involve particles that are made up of quarks, which are known as hadrons. Leptons, such as the electron, muon, and tauon, are still observed as free particles or interacting particles in nature. Therefore, the processes that are described with leptons, they are directly described by the standard model. With hadrons, it is more indirect, as I mentioned earlier. However, one way or another, any interactions and any transformations that we observe in nature, whether they occur at small distances or at large distances, are explained by the standard model. In this regard, the standard model stands as the pinnacle of the entire structure of particle physics, and in a broader sense, it represents the pinnacle of all fundamental physics. This is because it describes the most fundamental laws of nature that we are aware of today. Now, what are the characteristics of the particles that are part of the standard model? To begin with, we typically describe the quantum world using what are known as quantum numbers. An example of a quantum number is the electric charge. The electric charge is a fundamental characteristic of a particle that we understand quite well. Particles can be positively charged, negatively charged, or not charged at all. In fact, electric charge is a quantum number that is conserved in nature. The conservation of electric charge in the standard model is explained by the corresponding symmetry group. The principle of conservation of electric charge arises from the inherent symmetry present within the theoretical framework. However, this isn't the sole defining feature of particles, as we are aware that the standard model encompasses 3 distinct symmetry groups. The strong interactions are responsible for describing objects that are colored. The term color here is, of course, a conceptual label. It's simply a quantum number that can take on 3 different values, making it useful to refer to as color. This is done for the sake of clarity. Therefore, the colored charge is also associated with a symmetry group, and it too represents a conserved quantity. The color charge of quarks remains conserved. In weak interactions, there's a unique charge known as the left isospin. This name might seem a bit complex, but it has historical reasons and is a trait of weak interactions, being a charge that is conserved. Consequently, all particles possess quantum numbers or charges that are conserved, as dictated by the symmetry of the standard model. Within the standard model, there are properties that initially might not appear very obvious. Well, for instance, when discussing quarks, we often state that quarks are not observable in a free state. In other words, we are so confident that quarks are present within hadrons that the inability to directly observe them no longer appears unusual to us. The properties of these particles are well verified by experiments confirming the standard model. Some characteristics aren't obvious. For instance, the standard model describes particle masses and their transitions into other particles, maintaining symmetries. Here's an interesting example of weak interactions where several symmetries are broken. Well, specifically, it involves spatial parity violation or charge conjugation violation, where a particle transforms into an antiparticle. What else is part of the standard model? Besides quarks and leptons, the standard model also includes the Higgs boson. The Higgs boson emerged in the theory because it was essential to discover a mechanism that would provide mass to all the particles in the standard model. This was accomplished through spontaneous symmetry breaking by introducing an additional scalar field into the theory, that has spin zero, known as the Higgs boson. Therefore, the complete composition of the fields in the standard model includes 6 quarks, 6 leptons, 1 Higgs boson, and carriers of all 3 interaction types. Every one of these particles has been discovered through experiments. The most recent particle to be discovered was the Higgs boson, which was found in 2012. All the other particles were discovered during the 20th century. The last one from that period to be discovered was the neutrino, specifically the tyionic neutrino, which is the third neutrino, and it was discovered in 2000. This year marks a significant milestone. The 20th century has successfully completed the standard model, except for the Higgs boson, with all other particles being experimentally confirmed. This brings up an intriguing question. Does the story truly end here? Or perhaps, are there additional particles that have not yet been incorporated into the standard model, but eventually must be? Alternatively, could there be something entirely different that the standard model does not describe? There are numerous potential answers to these questions. We don't know the truth yet. Well, first of all, if we talk about new particles, like new quarks and new leptons, which have not been discovered yet. As I said, there are 3 generations of these particles in the standard model. The question is there a 4th generation? Experimentally, there is no 4th generation visible. Moreover, there is indirect evidence, both related to particle physics experiments and in cosmology, that there may not be a 4th generation. The point is that in the standard model, there is a so-called quark-lepton symmetry. There are as many quarks as there are leptons. But on leptons, more precisely on neutrinos, there are restrictions from cosmology that the number of independent fields of neutrinos is equal to 3. There is a small loophole for the 4th, but in all probability it will be closed soon. So, if the number of neutrinos is 3, there is a quark-lepton symmetry. Then the number of generations of all other particles is 3, and thus we have completed in this plan the standard model. The Higgs boson. I said there is only one. Can there be 2 or 4 or more? The answer is also the same. It's possible. Maybe there are other Higgs bosons. Perhaps we've only discovered one so far. But the theory allows for the presence of a large number of Higgs bosons. Whether there are or not is a question of experiment. In this sense, it may be that the standard model is not yet complete. New particles will still be discovered. But maybe not. A single boson can give mass to all particles. New interactions. We discussed 3 types of interactions in the standard model. They are realized as exchanges of carriers, gauge fields with unit spins. In a way, the Higgs boson is like a carrier of the 4th interaction, acting with spin 0. But is there more? Are there not some new interactions or some new symmetry groups broader than the standard model? Isn't the standard model part of some more general theory? This is also an open question. It is possible that it does. It is possible that it is part of a more general theory, but this has not yet been seen. It should be said that when we say that the standard model has triumphantly come to an end, we are saying that all, without exception, experiments that are put on the accelerators in underground physics and in space are all brilliant with absolutely enviable precision. The standard model is often described with an accuracy reaching up to 10 decimal places. In this sense, it's a truly unique model that enables us to describe a vast portion of nature, specifically inanimate nature, using very simple and universal mathematical forms. The triumph of the standard model of fundamental interactions, which perhaps now should be referred to as the standard theory of fundamental interactions, might give the impression that every problem has been solved. However, this is definitely not the case. It would actually be quite boring if they were all solved. So, What problems still remain? Well, first of all, there are issues within the model itself, because numerous questions still linger, such as why? Secondly, there are still natural phenomena that likely fall outside the standard model, or perhaps we just don't yet fully understand how to explain them. It is true, it must be said that all these phenomena of nature that require an explanation do go a little bit beyond elementary particle physics. They have mostly come to us recently from cosmology. Particle physics' own problems are perfectly described in the standard model, but many questions remain as to why. Let's start with the why questions. Why 3 generations of particles of the standard model? Why would nature require 2 copies of the generation that constitutes the entire world surrounding us? Initially, we believed those generations simply didn't exist. The particles we observe are considered elementary particles. However, it turned out they were not. Cosmic rays and accelerators somehow managed to produce duplicates. So, the question arises, why is there a necessity for 3 copies of the world we observe? Another intriguing question is that we have 3 types of interactions. Why does nature require 3 different kinds of interactions? Why specifically 3? And why are these particular 3 needed? We can, of course, approach this question through the so-called anthropic principle. This means that for humanity to exist and thrive, these 3 types of interactions are essential. This is indeed correct, it is true. For instance, we obtain energy, as we are aware, from the sun. It is delivered to us by the rays of the sun. That is nothing but electromagnetic interaction. You and I walk on the earth, attracted to it by gravity. That is gravitational interaction. That's the 4th one. We need that too. We're made up of atoms. Inside an atom, there's an atomic nucleus. Protons and neutrons would fly apart if they weren't held together by something. That's the strong interaction. So for there to be atoms, for there to be bodies, for there to be you and me, there has to be a strong interaction. The weak interaction is what causes decay. You might think that's its primary purpose, right? But actually, it's not. For the sun to shine, a thermonuclear reaction must occur. These reactions are decay processes, which are weak interactions. Without a weak interaction, the sun wouldn't shine. So we actually need all the interactions that exist. However, the question remains, could there be something else? Maybe we don't understand everything yet. Maybe we don't see everything. Einstein once dreamed of creating a unified theory. Electromagnetic interaction and gravitational interaction were known then. So he tried to create a unified theory of electromagnetism and gravity. But, as we know, it didn't work. Now we know that there's also a weak electromagnetic. So it is time to create a unified theory of the 3 interactions included in the standard model and gravitation. Is there such a unified theory? There are many different ideas. There is even a name for it, the grand unification theory, which unites the strong and weak electromagnetic interactions. Whether this theory is correct or not, we still do not know. There are theories that aim to unify gravity as well. These theories are even more intriguing, more complex, and even more difficult to comprehend. At times, the term theory of everything is used to describe them. For instance, string theory, which is a type of generalization of quantum field theory involving extended objects, at one point claimed it could construct such a unified theory of everything. It has also not succeeded thus far, but it is possible that we simply have not yet discovered the correct formulation. Therefore, going beyond the standard ideas might necessitate some intriguing and innovative solutions that will enable us to construct a broader generalization of what we currently comprehend and are aware of. However, there are already existing problems that probably demand a new theoretical framework, and these issues arise from cosmology. The crucial point is that cosmology is now deeply connected with particle physics because, as it turned out, the events that occurred in the early universe, which dictated the universe's development, are indeed described of the essence of particle physics. One of the intriguing problems that emerge from cosmology, a fascinating issue that is being widely discussed now, is the problem of dark matter. Cosmology tells us that besides the ordinary matter we can observe, such as stars, galaxies, stardust, and similar entities, there exists another type of matter that does not emit any light and is electrically neutral. This is what we refer to as dark matter. And so, looking back at the standard model of fundamental interactions, we have to answer the question of where dark matter came from and what particles it might consist of. There doesn't seem to be a suitable candidate for this role in the standard model. This means that if dark matter is described by a particle, which is very likely it is some new particle that is not included in our standard set, this mystery has yet to be solved. And to find such a particle, to find it experimentally, to find a theoretical explanation for it, of this particle. Another issue that emerged from cosmology is that in the early universe there was an equal number of particles and antiparticles created. That is, if, for instance, hydrogen was formed, then antihydrogen would also need to be formed. If helium was created, then antihelium would have to be created too. If iron was formed, then anti-iron would have to be formed as well, and everything should be equal. Yet, as we know, when particles and antiparticles meet, they convert into pure energy, which means light. This implies that if there were a sufficient amount of matter and antimatter present in the world, they would occasionally collide and appear, which we do not observe happening. Furthermore, we do not observe antimatter at all. We only see matter in the visible part of the universe. This brings up a natural question. What occurred? Where did the so-called baryon asymmetry of the universe come from, that we observe baryons and do not see antibaryons? This problem in the standard model of fundamental interactions is generally speaking solved. It is solved by the so-called combined parity violation, by some parameter called phase, which is responsible for the CP violation, and also for the aboronic asymmetry of the universe. But the mechanism of the aboronic asymmetry of the universe is still not understood. It remains a mystery, although it is clear to everyone that somehow it must be explained. Otherwise, our universe would not exist as it does. Now, there are simpler questions we haven't answered yet. For instance, the enigmatic neutrino particle fascinates many. It's mysterious because it's hard to detect. The nature of this particle isn't fully understood. Its mass is also unknown. Even with all the tools in the standard model, it remains a bit mysterious to us. In all likelihood, experiments conducted in the upcoming years will enable this mystery to be fully unraveled. We will gain a precise understanding of what the neutrino particle truly is, what its mass is, and whether it acts as an antiparticle to itself or not. In that sense, our comprehension of the standard model in this particular aspect will be complete. However, there remains one more enigma, perhaps the most challenging problem that confronts us in the realm of particle physics and cosmology so far. It's another related problem known as dark energy. But what exactly is it? The main point is that our world is filled with matter, and we can measure how much of this matter exists. It turns out that the quantity of matter dictates the curvature of the space we inhabit. When the density of matter matches a critical density, space is flat. If the energy density is less than this critical point, then space becomes open, similar to a saddle, and has negative curvature. If the energy density is above the critical energy density, then space is closed and resembles the shape of a sphere. So, when we measure all the matter in the universe and add it up, it gives a density that is noticeably below the critical density, indicating that we live in an open world. But then there's the presence of dark matter. Cosmological data reveals that there is about 4 times the amount of dark matter compared to ordinary matter. So, when we add together the ordinary observable matter and the mysterious dark matter, we find that it's still not dense enough to be considered critical. It's still only about 30%. It seems like we might exist in an open universe, but actually that's not the case. You can measure the curvature of space in a manner similar to how we do it in school, you could say. You can measure the sum of the angles in a triangle. As we know, in Euclidean geometry or plane geometry, the sum of the angles in a triangle is 180 degrees. If we are on a sphere, the sum of the angles of a triangle is greater than 180 degrees. If we are in a saddle, the sum of the angles will be less than 180 degrees. That is, we can find out what the curvature of our world is by measuring the sum of the angles of a triangle. But the triangle has to be very large. You have to sort of divide the points at the top of the triangle to different ends of the universe. And now imagine that such an experiment was done, and the sum of the angles of the triangle was measured. It relates to measuring what's known as relic microwave radiation. When this was measured, it was discovered that the sum of the angles in a triangle is about 180 degrees. This indicates that we exist in a world that is approximately flat. Therefore, the question arises, what constitutes the remaining 70% of the density? This is referred to as dark energy. It's a mysterious substance about which we currently have no knowledge, but it definitely calls for an explanation. It requires a detailed explanation of the presence of this substance, including what it consists of, how it is described, and the reasons why it is described this way. Often this substance is referred to by what's known as the cosmological constant in the Einstein equation. Einstein himself introduced this cosmological constant. It's not the sole explanation for the dark energy that exists, but I would say it's a very natural explanation. Therefore, to accurately describe the correct amount of dark energy, to achieve this 70%, the cosmological constant must have a definite values. It turns out that it appears to be such that it is about 100 orders of magnitude smaller than what we would expect. In other words, if we were to naively start calculating this value, we would be off by 100 orders of magnitude, full of catastrophe, naturally. This is perhaps the biggest mystery we currently face. It exists as if in the realm of fundamental physics. And since particle physics claims to be the fundamental physics that describes all the phenomena of nature along with gravitation, then this riddle of elementary particle physics, cosmology, gravitation theory, unified theory, all of them together should solve this riddle and solve this problem. So far, it remains the main unsolved problem of fundamental physics.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.